Hi, everyone. Charlie Marsh is the founder of Astral, a company building high-performance developer tools for the Python ecosystem. Over the past 2 years, he's released Rough, a Python lintern auto-formatter, and UV, a Python package and project manager. Both projects have grown to tens of millions of downloads per month and have seen rapid adoption across both open source and enterprise.
Okay, everyone can hear me? Okay, great, excellent. Wow, very nice intro. Now what am I going to do with my own intro slides? My name is Charlie. I'm the founder of Astral. Me and my team, we spend our time trying to build really fast Python tooling in Rust. We're primarily known for 2 tools, right? The first of which is Rough, which is a linter, formatter, and code transformation tool. So you can use it to format your code, but also to identify issues like unused imports and fix them automatically. And the second, which is going to be the focus of what I'm talking about today, is UV, which is our Python package manager. I gave a talk at PyCon about Rough, and it sort of covered like what Rough is, a little bit of how it works, and then what makes it fast. This is going to be similar, but focused on UV. So I want to talk through what UV is. I'll try to keep that short because it's maybe the least interesting part. Why we built it, some of the hard problems that went into building it, and then end with a couple examples or sort of case studies of things we did that make it really fast, because that's the thing that we tend to get the most questions about, is why is it fast? So UV is what I would call a fast all-in-one Python package manager. So you can use UV to install Python itself, create virtual environments, resolve dependencies, install packages, of course, it is a package manager. You can use it to build your own Python packages that you would then like upload and redistribute. So UV is, if you're familiar with the Python ecosystem, you could think it as a drop-in alternative to tools like pip, pipex, pyenv, virtualenv, poetry. And it's not a replacement for any one of these. It's really intended to be a replacement for all of them. So we model what we're trying to do with UV after Cargo. So if you've worked in the Rust ecosystem, the tooling is very streamlined and very unified. And the way I would describe it is I feel like Rust tooling, oh no. Okay. Hold on. Okay, the way I think of it is that Rust tooling is very high confidence. Like when I clone a Rust project, I'm very confident that I can run it. It will run successfully, and I know how to run it. And we're trying to get to a similar experience with UV for Python tooling. So UV is this single static binary that ideally gives you everything you need to be productive with Python. You install UV, and then everything is sort of taken care of for you. So UV does a lot of stuff, and it does it all while being just way, way faster than a lot of the other tools in the ecosystem. And when we started, I knew when we started working on a package manager, and this was some of the reaction, that it would be a little bit of this, because in the Python ecosystem, there's just a lot of different tools for packaging. And so when you come out and say, hey, we finally built a Python package manager, there's a lot of, well, this cartoon. And we still see a little bit of this, actually, which is kind of funny to me because the tool is pretty popular. But I think UV is actually pretty different from a lot of the other things that exist in the ecosystem in the previous attempts to build this tool for Python, primarily for 2 reasons. One is just like the scope of what we're trying to do. So I mentioned this before, or hinted at least, like Python tooling is very fragmented. And I think of that in like 2 ways. One is, for anything you want to do, there's like a bunch of different options, and it's very hard to choose and know which one you should use. And the second dimension is, like, for anything that you're trying to do that's non-trivial, you have to like chain together a bunch of tools. And for UV, it's meant to be like a totally unified stack. So we didn't like build on top of anything else, right? We didn't like build on top of pip or inherit any of the baggage that comes from existing Python tooling. We built like everything from scratch. And that creates a really powerful model, both in terms of like the user experience we can deliver, but also how good it can be, I guess, internally. The second reason I think that it's a little bit different is just the performance, right? Like UV, as I mentioned, it's very, very fast. And the thing that I've seen in my time working on this stuff is that when things are like way, way faster, they really change like the user's relationship to the tool and even like the way that they work with it. So like we saw this in Rough, where jobs that people like used to only be able to run in CI, they can now make like pre-commit hooks because like the speed differences were just so different. And so suddenly this thing that you like dread running is something that you can just like do locally and get and pass. And with UV, another analogy would be like virtual environments. Like in Python, often like you have a virtual environment on your machine, it's in like a certain state, and you really don't want to mess it up because you won't be able to recreate it and like get it into that place, or it's really expensive to recreate because it has all these packages installed. But with UV, like destroying and creating a virtual environment is extremely fast. Like we try to view them as totally ephemeral. Like you can just destroy them and recreate them because it's so cheap. So we're actually trying to change, like it's not just about, there's a lot of obvious nice things that come with being much faster, but I also think that it can just change a lot of the workflows around how people work with Python. We released UV in like mid-February. And since then, it's just grown a lot. So it's at like 16 million downloads a month. It's now more than 10% of the requests to PyPI come from people running UV, which is kind of crazy. Like I would have been happy maybe with like 1%, just because the sheer volume of what people are doing with Python is pretty wild. So that's been a cool thing to see. We have a lot of stars, we have contributors, blah, blah, blah. But the point is, we built this thing. I consider it fairly well battle tested. It's been used across the industry. So hopefully the stuff I say has some credibility behind it. All right, so the main job, right, or the main thing you do with a package manager is you install packages. So I just want to talk through the life cycle of what happens when you run a command to install packages with UV. And UV has two primary interfaces that you can use to engage with it. The first is that we have like a pip compatible interface. So if you've run like pip install, you can just run like UV pip install, and we implement a lot of the same commands that pip would, which is great for people who want to adopt it without changing their workflow, although we would like their workflow to change, obviously. And the second is we have these higher level commands like UV sync and UV lock that you sort of declare your dependencies, and then we just take care of everything and make sure the environment is in the right state whenever you want to do anything. But they both operate under a fairly similar life cycle, right? So the first thing we have to do is we have to like find the user's Python interpreter. UV does not depend on Python, but we do like need a Python interpreter in order to do a lot of useful things. So like if you want to create a virtual environment, for example, a virtual environment has to symlink in a Python interpreter. So like we can create a virtual environment, but we wouldn't have a Python to put in it. And we need to know things like what version of Python are you running, like what platform are you on, all that kind of stuff. So this is actually pretty hard, but really not very interesting. The next thing we need to do, right, is we need to discover the actual user requirements. This is the user telling us like the state they want to be in at the end of the command. And that could be, they gave it to us directly. Maybe we read it from a requirements.txt file, something similar. Given those requirements, we resolve them into, this is the core job of a package manager. You give us some requirements, and we try and figure out a set of versions that satisfy those requirements. So the user might say, I want Pydantic, and that's not really enough information on its own, right, for us to like what does it mean for the user to want Pydantic? So the first thing we have to do is we have to resolve that into a set of versions such that everyone's dependencies are satisfied and all the versions are compatible. And ideally, it's like the latest version of Pydantic too, because that's what the user asked for. So even this isn't like quite enough information for us to really do anything, because this just describes the packages and the versions, but it doesn't really tell us anything about like where to get them. So ultimately, this is not what we're trying to produce. We're trying to produce something that looks more like this. So UV ultimately will create a lock file, and that lock file represents a resolution. And in that lock file, we have information, like this is one entry from a lock file. So we have like the package name, the version, but we also have information about where it came from, also the packages it depends on. We have like a SHA, we have file size, et cetera, et cetera. So ultimately, like when we resolve, we're trying to create something like this. And I'll talk more about like how this is structured in a bit. Once we have that graph, we come up with a term I made up, like an install plan. The idea is like we know the state that the user wants to get to, which is like represented by the lock file. We have to look at the current state of the user's machine. Like maybe they have like an old version of Pydantic installed, so we need to like uninstall it and then install the newer version of Pydantic. So most of the, well, not all, but most of the interesting work happens in here, in the actual resolver. And this was also, I think, the hardest part of building UV. So I want to talk about a couple of the hard problems that are maybe like non-obvious, especially if you don't spend a lot of time like thinking about Python packaging, which I hope like most of you don't. So the first thing that makes this problem quite hard is that Python has no multi-version support. So you cannot have two versions of the same package installed at the same time. This might sound like a very obvious, so you can't have like Pydantic version 1 and Pydantic version 2 installed at the same time. This might sound obvious, but actually like a lot of languages do support this, so like Rust and Node will let you do this without any issues. In Python, it's basically a limitation of the runtime. There's like, imports are like a global cache keyed by module name, so like you can't have multiple modules with the same name. So as like a concrete example, let's say the root is like our project, and we depend on like a specific version of VLLM, and we also depend on a specific version of LangChain. And VLLM depends on Pydantic 2, but like this old version of LangChain does not work with Pydantic 2. It requires Pydantic version 1. So like this is not a solvable graph in Python. You cannot satisfy these dependencies. And if you try to give this to UV, you'll get this pretty error message that tells you this doesn't work because you have these two dependencies and they have an incompatible Pydantic requirement. So instead, imagine that the user says like, I'll accept any version of VLLM, but I still need this like old version of Pydantic. In that case, what we need to do, right, is we need to backtrack and we need to test out all the versions of VLLM and try to find a version of VLLM that does work. So eventually we go and find, the previous version was like VLLM 0.6.1, I think. So we tried out a bunch of versions. Eventually we find a set of compatible requirements. And when we do this solve, right, it's typically not just like these 4 packages. Like this is just a snapshot of like ultimately the resolved graph from those set of dependencies, right? Like it's typically a sprawling thing with lots of different requirements, and there's lots of different ways to satisfy it. And ultimately, I mean, like the shape of this problem might look familiar to some of you. We're trying to do version solving. So like given we have a universe of package versions, they have constraints, like some things depend on different versions of Pydantic. We need to find the set such that like all the dependencies are satisfied. We can only have one version of every package. And also we don't want to have like extraneous packages. And this is a Boolean satisfiability problem. It is NP hard, so I like to think that it's quite hard. And I'm not going to go into the details of like exactly what our solver looks like, but if you think back to school, we use a SAT solver. It's based on CDCL, which is like conflict-driven clause learning. It's basically just a fancy thing that tries to solve those graphs in as efficient a way as it can by exploiting heuristics and things that it can learn. But it can be exponential. Like there's no guarantee that it's actually going to solve it in a reasonable amount of time. So because we don't have multi-version support, we have to do this SAT solve. If we had multi-version support, by the way, like we wouldn't necessarily have to do that. Like Rust, like Cargo's solver, it's not a SAT solver. Like it does like a graph traversal, but if you get to a hard place where like things are not quite working, like you can kind of just bail out and say like, let's add 2 versions of this package. So that like escape valve exists, but it does not exist in Python. And this is also true of other languages. Okay, second thing, and I've never tried to explain this. This is all new material, by the way, and this in particular I've never tried to explain to a group of people, so I might, let me know afterwards if it makes any sense. This was like surprisingly, or parts of this were surprising, but this is maybe like the hardest part of building this resolver, which is Python has this like very rich syntax for declaring requirements that should only be installed on certain Python versions or only on certain platforms, et cetera, et cetera. So like just as an example, these are the dependencies of a real package. I can't remember what, maybe Flask. And you see the last one has the import lib package should only be installed if the user's Python version is 3.10 or earlier. And if we look at some of the transitive dependencies here, like click itself depends on Colorama, but only on Windows. And it also depends on import lib, but only if the Python version is less than 3.8. So when you see this like set of requirements, there's kind of two ways to think about solving the graph. Like one is solving the graph for like a specific user at a specific point in time that's on a specific computer, right? So maybe a user comes up and they're using Windows on Python 3.12. So like some things here are relevant and some things aren't. That's actually pretty easy because you're basically just filtering things out while you solve. It's not a huge problem. But we want to solve a slightly different problem, which is we want to generate a lock file that like any user on any machine can then use to get a reproducible install. And what that means is like, if a user is on Windows and a user is on Mac, they may not get the exact same set of packages. Like the user on Windows would get Colorama, the user on Mac would not. But like all the users on Windows on the same Python version should get the same set of packages. And ideally, like the differences between those users are as small as possible. That's not actually something we guarantee, but the gist of it is you want to be able to take the lock file, and like any user on any machine should be able to take it and install. Like we don't just want a lock file for Windows 3.12. We want what we would call like a universal lock file. And that problem is like a lot harder. So again, like the core of our solver is the SAT solver. And then there are kind of like two pieces that go into trying to build this universal resolution. So one is that at a high level, we kind of try to find a solution that works on all platforms. Like effectively, we assume that all of those markers are true and try to see if we can find a solution. So like the marker that said Colorama, like only on Windows, we would basically say, let's just assume that's true and see if we can find a solution. And then afterwards, we'll like filter out the packages that are only for Windows. So that's good, but the problem is, right, you can have these conflicting dependencies. So like this is totally valid. Like you could have a user say, it has to be Pydantic 2 on Windows, but it cannot be Pydantic 2 on all other platforms. And again, we're trying to find a solution such that a user shows up and they're on Windows, they install, they get Pydantic version 2. A user shows up and they're on Mac, they get Pydantic version less than 2. Okay, so the way that we solve this is and again, we've made up all this terminology because I don't really know if there was good terminology for it that existed. But what we do is we basically try and fork and solve the two graphs separately. So, in this case, on the left, we would try to solve like Pydantic greater than 2, assume we're on Windows basically, and just solve the rest of the graph. On the right, we would do the same thing. The graph ends up being like a lot simpler, but we would solve these two graphs like effectively independently. And then we merge the results back together. So this is like the merged resolution of taking those two. And oh, wow, great. Oh, it's all, okay. I messed up the transitions on this slide, but I think we'll be okay. Okay, this is what this is supposed to look like. So basically, right, the thing on the bottom right is like the merged resolution. And on the two sides, we have like the platform-specific resolutions. So annotated types needs to be included, but only on Windows, because it was only present in the Windows resolution. I think this is going to do it on like all of these. Okay. Pydantic is included twice, right? But once for Windows and once for non-Windows. And those markers are disjoint. Like there's no overlap on them. So everyone will get one version of Pydantic, but it will be like one of these two. And then, importantly, there's also a package that's included in both resolutions. So typing extensions is included both on Windows and on not Windows. And sorry, I know this is like super annoying. So if you look at like the way that marker gets constructed, we have typing extensions, and we're saying we want to include it on like Windows, but also include it on not Windows, right? And that marker, like these come from these two different places, and that marker is always true, right? So we can actually just ignore it completely. That's why it's not present in the final resolution. So not only do we have to like solve these graphs in this way, but we end up doing a lot of different, there's this whole marker algebra that we have to consider, like the ors and the ands that you're seeing there. We have to do a lot of operations. Like here, evaluating that marker always, or figuring out that marker always evaluates to true, and that we can just omit it. Like, I mean, it's easy in that case, but like we'll see, some hard cases. Similarly, we have to be able to test for disjointness with these. I mentioned that like we had the two Pydantic requirements and they were disjoint. That just means that like they can never both be true, effectively. So for example, maybe we're like doing the solve on the left side of the previous slide, like we're solving for Windows, and then we like see a dependency that has this marker on it. We want to know like, is this dependency relevant? Like we know we're solving for Windows. So like, should we even care about this dependency because it's only applicable on these platforms? Right, and that question is basically, can they both be true? Are they disjoint? This is also a Boolean satisfiability problem. And the markers can be like pretty complicated, right? This is also NP-hard, like totally separate NP-hard problem, which is we have to be able to test, I'll go back one. We have to be able to test whether like these two Boolean expressions are disjoint. And we're doing this like all the time. Now most markers are pretty simple, which is great. But like these are just some examples of, these are like the fully simplified markers for like a real example from our test case. This is resolving, if any of you use like transformers, like the Hugging Face project, one of our test cases is we take that project and we enable all of the optional dependencies, which like no one should do, but it creates like a very, very large graph, and so it's one of our harder test cases, and like these are the fully simplified markers. You can see like some of them are pretty large. By the way, before we did this marker simplification of trying to get to like these simplified normalized forms, we would do that resolution, and like each dependency would have like tens of kilobytes of markers. Like the marker expressions were huge. And that was we even had like some very basic heuristics, like, just kind of like simple stuff for trying to normalize and filter them out. Ultimately, someone on the team wrote this like marker normalizer based on a technique called algebraic decision diagrams. It's like a totally separate solver that we had to build to try and normalize those markers and ask questions like, are they disjoint? So these were both like very, very hard problems. A third that I'll just mention briefly is that, and I'm not actually like going to talk about this one that much, but I do like to complain about it a little bit. So in the Python ecosystem, there's really like no guarantee that you have static metadata for a package or like a dependency you want to resolve. And by that I mean like if we're trying to resolve Pydantic version 2, we're going to go to the registry and we're going to say like, what's the metadata for Pydantic version 2? And it's actually not guaranteed that they will be able to give us an answer. Ultimately, what might happen is we might have to run some sort of arbitrary Python code in order to get the dependencies. Basically, if they publish a built distribution, it'll have dependencies, but if they only publish the source for the package, we might have to effectively like pull that down and run, if you've ever seen like a setup.py file before, we have to like run a setup.py file. We might have to build the whole package even just to get the dependencies. So we do a lot of things to try and avoid doing that while still being correct. And I'll talk about some of those in a bit. But kind of like just concluding on this section, like ultimately what we're trying to build here, we model it as a graph, right? The nodes are packages at specific versions, and the edges are weighted by markers. So in this case, we have like the two versions of Pydantic, but one edge is weighted by only being on Windows, the other is like never being on Windows. And you can see they like share some common nodes, et cetera, et cetera. And like the nice thing about this representation is when a user comes along and wants to install on Linux or whatever, we're just doing a direct graph traversal and saying like which edges are relevant and which are not. So there are some tools in the Python ecosystem that try to do this, but they then have to do like a separate sat solve at install time. So they have like a set of packages, and then when you install, they actually have to like run a sat solver to figure out the right versions. We have the nice property that like it's just, there's no like second resolution when you install. We're just like traversing this graph and figuring out the things to include. So this is like the ultimate goal. Like all that work goes into trying to produce this thing. Okay, so I talked a lot about some of the hard problems we had to solve to build this. Now I want to talk a little bit about things we did to make it fast. The first thing that comes to everyone's mind, and also that I just talk about a lot, is Rust. Like Rust is a big part of UV and of how we've made it so fast. Like UV is written in Rust. Like I said, we don't have a dependency on Python, although you do need to have Python installed. But the observation for me, this slide is slightly sort of just opinions. UV has gotten like faster and faster over time, like despite being written in Rust the whole time. So it's not just about being written in Rust. Like from my perspective, I think Rust gives you a really fast baseline. And then it gives you a lot of tools that you need if you want to write really, really fast programs. And like other programming languages can expose these too. But for example, it's pretty hard to like care deeply about memory allocation if you're writing Python. Like you just don't really have a lot of control over what's happening. Whereas in Rust, you're actually like forced to care about a lot of those things, right? Which some people will complain about, but it is ultimately one of the strengths of the language. So like Rust is part of it, and I'm going to talk about some parts of Rust that we use. But UV is also, like most package managers, like a lot of what we do is I/O, and Rust is like only so helpful with I/O. There's like a lot of other things we need to do. So it's not, Rust is a big part of UV, but it's not all about Rust. I do want to start though with an example that I think illustrates like why Rust is helpful and important. And you can do this in other languages too, but we do it in Rust, so that's what I'm going to talk about. Okay, version parsing. Okay, so like in Python, like every package has a version, right? And you could have a very simple version, like 1.0.0, but they can get very complicated. So you can have like pre-releases. That can be like alpha, beta, or RC, which is release candidate. And the pre-release can have a number. You can have like beta 1, beta 2, beta 3. You can also have post-releases. So like if you need to update, this would typically be like, if you need to update the documentation but not the source code, you might do like a post-release. Like the contents are the same, but you had to release it again for some reason. Okay, there's also this piece called like the local version identifier, which if you've ever worked with PyTorch, you will probably be familiar with this. This is intended for, I'll probably get this wrong, but at least in the spec at least, it's intended for like you're building a package locally and you want to be able to tag it in some way like on your local machine. PyTorch has now used this due to other limitations in the packaging ecosystem to mark packages as being compatible with certain accelerators. So like you might have to build a lot of different versions of PyTorch that support different versions of CUDA. And they now use this part of the identifier just because it was sort of an open, like a free space to indicate that, because there's no other support in the standards for like marking packages as compatible with an accelerator. It's sort of a hole in the standards. So anyway, this has become very popular now in the Python ecosystem. Okay, this one, I actually like forgot this one existed, and then I was doing the slides. You can do this like epoch thing. I actually don't really remember what this is for, but you can put like a number and then an exclamation mark. And that's a valid Python version. And of course, you can actually like compose these things together. Like you can have like a post-release of a pre-release. I'm pretty sure you can have like a local version of a pre-release, et cetera, et cetera. So like representing these is pretty hard. Like it's very rich syntax. So like the full representation of this is something like this, right? We have like multiple vectors, which means we're going to be allocating memory. Because the release segments, there can be more than 3. There can be like as many as you want, actually. Like it can be 1.1.1.1.1, like that's fine. You can have multiple of those local segments, like you can have like plus something, blah, blah, blah. So like this is pretty heavy. And we are dealing with these things like all over the place. So someone on our team, he goes by Burnt Sushi online, so I should credit him because he figured this out. He noticed that we can represent like over 90% of versions with like a single U64. Which is great because one, it's like fully stack allocated, and there's a second property that's really nice about it that I'll get to in a second. But this is actually what we use internally. So like internally we have a version, and then we have an enum, and we try to represent most versions as like this version small, and then we represent things with the full version if they don't fit into that scheme. So I think it works. So it's a U64, so we have like 8 bytes to work with, okay? 8 bytes of space. So the first 2, or the first or last 2 bytes, however you want to think about it, bytes 6 and 7 refer to the first release segment. So like when we had 1.0.0, that would be the 1. And that's because calendar versioning is still fairly popular in the Python ecosystem. So we need 2 bytes for the first release segment because people would have packages that have a version like 2023.1, 2023.4, et cetera. Okay, the next 3 bytes just represent like the second, third, and fourth release segment. And then the 3 bytes at the end represent one of a pre-release specifier or a post-release specifier. We do not try to even capture both of them in this representation. But the really nice thing about this, it's not just that it's cheap it's not just that it doesn't have to allocate memory. Like the really great thing is that greater versions map to larger integers. So like it's not just that we're parsing and creating these all the time, we're also comparing them constantly. Because we want to know, like, is this version greater than this version? Does this version satisfy like this version specifier? And now, like in this representation, you have to be very, very careful in how we construct the representation. But in this representation, answering that question is just a single memcomp. It's just like, is this U64 greater than this other U64? As opposed to dealing with those two big version things that have vectors, and we have to like understand like blah, blah, blah. So like most of the implementation of this is actually like a huge comment explaining how explaining the representation, how it works. It does have limitations, right? We can't support that epoch thing. You can't have more than 4 release segments, like 1.1.1.1. But again, over 90% of versions can be modeled this way. And yeah, this is actually something we did. And like when there's minimal I/O, so like everything's fully cached, and we have this very hard resolution that has to do a lot of package version testing, it sped things up like 3 or 4 times. It was like super, super impactful because this is where we were just spending a ton of time parsing versions, allocating memory for them, and comparing them. So again, this is just like, you can do this with other languages too, but Rust, I think, is very amenable to doing this kind of thing, and it made a really big difference for us. I mentioned that a lot of what we have to do with the package manager is actually I/O. So I want to have go through 1 or 2 examples of ways that we try and cheat a little bit with I/O. So I hinted at this before, but when you want to understand the metadata for a package, like you need to know its dependencies. It's not guaranteed that you can actually get that information without like running some Python code, but often you can. So when you publish a package to the index, there are 2 kinds of packages. One is a source package, and one is a built distribution. And the built distributions are probably like most of what you interact with. And those are really important because when you interact with Python, a lot of what you're doing is actually interacting with native code, right? So if you use like NumPy or SciPy or whatever, those have to be built on a bunch of different platforms because they are not pure Python. So Python has this extensive support for built distributions. And built distributions do include the metadata, which is great. The built distributions are actually just zip archives. They're called wheels. I don't fully understand why, but the suffix is .whl, but it's actually just a zip file. And like somewhere in the zip file, there's a metadata file, like literally a file called metadata that contains the metadata for the package. Some registries will let you ask for this directly, but like a lot of them won't. It just depends on the registry. Like PyPI, the public index, will let you just say like, give me the metadata. But like for whatever reason, a lot of the commercial registries do not support this yet. So we want to like get the metadata, but we don't want to download the whole wheel because the wheel, like the PyTorch wheels, are like hundreds of megabytes. And we don't want to download them just to know the metadata because we might have to test like a bunch of versions too. So what we do instead, this is a representation of a zip file. I used to be very scared of file formats, but zip is very simple. It's sort of just a series of entries. Like each entry has like a header, and then it has the contents of the file. And then at the very end, there is what's called the central directory. It's kind of like an index. So the central directory knows what all the files are and where they're located. Like you can think of the zip file, it's just like a stream of bytes, and all the files are somewhere. The central directory knows where all the files are. So what we do is we first make a range request for the central directory. So we guess where it is. We say it's probably within this, this many bytes at the end of the file. And then we grab the central directory, which is basically an index of information. And that does not require downloading the whole wheel. We can ask the registry to just give us those n bytes at the end of the file. We then find the metadata file in the central directory, and then we make a second range request just for that metadata file, because the central directory knows where it is. So we grab the central directory, we figure out what we need to request, and then we go and get the metadata file. Yeah, this has nothing to do with Rust, right, by the way. like other Python tools can do this too, but it does save a lot of time because we don't have to download these huge files just to answer the question of like, what packages does it depend on? Probably the biggest contributor to like why UV is so fast and why it feels so fast is the cache design. So UV is, like the cache itself is all optimized for like warm operations, as in operations where you have the data you want in the cache and you just need to like get it into your environment. And that's because like like most of the time when you're installing a package, like you've probably installed it already on your machine at some point in time. That may not be true for like a continuous integration environment, but like on your machine, you probably have a lot of copies of the same packages that you've installed in different places. And so we try to optimize for those kinds of interactions where you have data in the cache, and we want to make it really fast for you to do something with it. So the way that we model this is we have this sort of global cache of unpacked archives. Recall, like every archive is a zip file. We don't actually store the zip files in the cache. What we do instead is, like, while we download those files, we just unzip them directly into the cache. So the cache contains like the fully unzipped contents of the files. And when we need to install, the installation operation is basically that we just, we use ref linking where we can, or hard linking. We just link the files into your environment. So like if you're using UV and you need NumPy in like a bunch of different environments, we just install it in one place. And then when you install it in your environment, we are basically just creating links to the files in the cache. That's like really, really fast, and it's also very space efficient because it means that you're not installing the same contents like over and over in all your different projects. So again, most installs are just like hard linking a bunch of files from the cache into your environment. So like this is just literally just a screenshot of like my file system of the cache. The cache looks like this, right? There's like packages, package versions, and then it's just the unzipped contents. And so when you want to install Rich in your virtual environment, we're just like creating symlinks to all these files effectively. And that's really, really fast, which is great. So like this alone contributes to a lot of the feeling of things being instant. Like if you've installed something on your machine, you reinstall with UV. This is like, a lot of it is due to how we design this cache and the fact that we try to optimize for those kinds of operations. Okay, last thing. So this is really good, but it only works for, this only applies to like files. A lot of what we need to store in the cache is like metadata. So maybe like blobs of data, right? Maybe we need to know like, what are all the available versions of like this package? This does not apply to that. So we use a slightly different trick for those cases, which is we use a technique called zero copy. And this will require the most Rust knowledge, but I'll try to avoid it. The intuition here is like, let's say that you have a struct, like this blob struct, and it has a field. And it's being stored as JSON. So like, if you want to deserialize this, you read the JSON file from disk into memory, and then you run like basically you run a parser, and then like you grab the contents and put them in the struct. The observation of zero copy though is like, and I don't know if anyone will know the difference between these two things, but when you're trying to create the struct, you already read the JSON file into memory. Right, so you already like allocated memory to read that file into a string. So you don't actually need to like allocate more memory to create that blob struct. The version on the left, that requires an allocation. So if we want to go from the thing at the top to the thing at the bottom, we have to allocate once to read the contents into memory, and then allocate again to create the struct. Instead, like we already know that the string is there verbatim in the contents. So ideally, instead, we could just create a pointer to it. So we read the JSON into memory, we parse it, and then we, ideally, this is sort of theoretical, right? We just like create a pointer to it rather than reallocating memory to create everything. So this is what we do, but we do it like sort of on steroids, I guess. Like the way it works is we store the data on disk in effectively the same representation that it will have in memory. And when we read it back, we're basically just doing like a pointer cast to go from read data to fully realized structs. We use a library for this called archive, which is very good. And there are some safety checks around this, of course. I mean, it's totally unsafe Rust, but like there are safety and validation checks you can do around this. But the really cool thing about this is like the deserialization does not scale with your data. So like you have to read the contents from disk, and like as you have more and more data, that file will be bigger and bigger, and like you have to read more and more. But going from the data that you read to like the fully, like the deserialized struct, that does not scale as the data gets larger. Unlike with JSON, right? Like with JSON, you would have to like parse it, right? You would have to go through all these operations that would get slower and slower as the data got bigger. Like the really cool thing about, in my opinion at least, about zero copy serialization is the deserialization does not scale with your data. So like it doesn't matter really like how big the struct is or how large that string is. Like it does matter for reading the data from disk, but it does not matter for deserializing it into memory. Okay, that was the last thing I was going to cover. I had a bunch of other things I want to talk about, but I just put links to them, and maybe I can share the slides. And I think that's it.